Hi, all engineers and architects. Today we are talking about good architecture and component decoupling in software systems. So I'm going to walk you through what makes software actually soft, what are the characteristics of good software, and how you can employ the principles of component coupling to build good architectures. At the end, I will give you some actionable steps for you to decouple your components to make your architecture better. Let's get started. What is the purpose of software? Software was introduced to easily change the behavior of machines because obviously hardware was hard to change. But if our architecture is so terrible, then that would make it hard to change the behavior of machines, essentially losing the purpose of software. Next, let's see what is the purpose of good architecture. A good architecture must obviously support the use cases of the system, and it should support operations, maintenance, development, and deployment of the system. Another very important purpose of good architecture is that it should facilitate to leave as many options open as possible for as long as possible. Let's see what I mean by each of these important aspects of the good architecture. So how does good architecture support use cases? The true intent of software should be visible at the architecture level. For instance, a student management system should look like a student management system when viewed at the architectural level. A payroll application should look like a payroll application when looked at an architecture level, without having to dive deep into each component of the application. Next, let's consider how a good architecture supports operations. Some of the operational aspects we need to consider are the number of transactions per second, number of parallel processes, number of parallel threads, and the number of simultaneous memory storage accesses, and how the communication should happen between each service. The number of transactions per second would vary significantly from a small student management system to a very busy online trading platform. Similarly, all these aspects of the operations would be very different in these two systems. So our architecture should be carefully designed in a way such that these operational aspects of the system are successfully met. If we design our architecture as monolithic, then it would be difficult to scale individual components of the applications as needs arise in the future. In contrast, if we design our architecture as microservices, then it would make it easy to scale individual components as services and ensure proper communication between these services. Next, we will see how a good architecture helps with maintenance. Maintenance cost is one of the most expensive cost types in a software system. There are two main types of maintenance costs, namely spelunking and risk. While spelunking cost is the cost involved with the developers reviewing the existing code and finding the best strategy to add a new feature or fix a bug, the risk cost is associated with the unexpected side effects introduced by those new features and bug fix implementations. So a well-thought architecture designed into a foreseeable future will keep as many options as open as possible for new feature delivery, making the maintenance an easy and convenient process for the developers, thus reducing the maintenance costs. Next, we are going to see how a good architecture supports development. Here we are learning another important law called Conway's law. It says that any organization that designs a system will produce a design whose structure is a copy of that organization's communication structure. What this means is that the way the organization's team communicates with each other will be reflected in the organization of components in the system and the way those components communicate with each other. This may not be true for a small organization, but if the application is developed by multiple teams where each team has several developers, it is natural for the architecture to be split into components so that each team can focus on one component without stepping onto each other's toes. Though it will not be the best option for the architecture in terms of maintenance, deployment, and operations, eventually the architecture will move towards that type of structure because it supports the development teams. The final aspect is the support for deployment. Essentially, the system should be easily deployable with a single action after a build. If you require a manual update in another component after a build, or if you require to manually update a secret store, a key value store before the deployment, or if you require to run a manual script before the deployment, these are all red flags that your architecture is not supporting deployment. This is where sometimes a microservices architecture will become a pain, because if you have a monolithic architecture, you can easily deploy your entire application after the build. But when you have different microservices, you might have certain dependencies that will prevent independent deployment and would require the deployment of another module or a manual update of another module before you can actually deploy the module you just built. Next, I would like to talk about the aspect of keeping options open. Yes, it is really good if we can keep all the options open for any new feature that will come in our way. But how do we know? There is significant uncertainty as to the future feature requirements, future team structures, future development and deployment requirements. But if we play a careful game, when decoupling layers in our architecture, maybe we could leave those options open for a reasonable future. A major mistake that we do is follow an architecture of an earlier system that we develop into the new system. Without much due consideration of the new system at the hand, we finalize, okay, we are moving with the relational databases. Okay, we are moving with the REST APIs. And fine, we are moving with the serverless backend at very early stage of system. These rigid architectural decisions that we make can significantly hinder the ability of our application to keep options open for a wide variety of feature requirements that will come in the future. When talking about keeping options open, we essentially need to talk about software decoupling. As suggested by Uncle Bob in his book of Clean Architecture, there are three ways you can decouple software, namely decoupling layers, decoupling use cases, and decoupling modes. Let's see each of these now. In decoupling layers, the objective is to divide the system into decoupled horizontal layers such as the UI, database, API, application-specific business rules, and application-independent business rules, etc. So how do we achieve this? Even though we don't know all the possible use cases of our system as architects, we know the basic intent of the system. We know if it is a payroll application or if it is a stock management application likewise. Now we can apply single responsibility principle and the common closure principle to separate those things that change for different reasons and to collect those things that change for the same reasons. For instance, the API changes for reasons that has nothing to do with business rules. So the business rules and API should be two separate layers. Also, in the business rules layer, we can identify certain rules that are application specific and certain rules that are application independent. So all these layers we can use to decouple our system. Next, we are talking about decoupling use cases. It is a natural way of decoupling a system. Use cases themselves change for different reasons and at different rates. For instance, adding an employee in a payroll system will change at a different rate and for different reasons than the use case for deleting an employee from the same system. These two different use cases will have different UIs, different databases, and different business rules. Thus, use cases allow us to create a vertical cut through the horizontal layers that we established before. This way, if we want to group the API and database for a particular use case, we can do that without impacting other use cases. Similarly, if we want to support new use cases, we can support them without affecting the old use cases. The other benefit of decoupling based on use cases is that if there is a particular use case that requires higher throughput, then they are automatically separated from the use cases that require lower throughput. That way, those components that require higher throughput could be placed on several servers, while those requiring lower throughput can be placed on a single or few servers. Finally, we are going to talk about decoupling modes. It is important to understand the difference between true duplication and accidental duplication. As professional programmers, we want to avoid duplicated code in our application. For instance, if we have the same user screen or if we have similar function, we tend to believe that we can remove the duplication by sharing a single user interface or by sharing a single function. The important question here is to ask whether those user interfaces or functions change for the same or different reasons. If those change for same reasons, then yes, it is true duplication and we can unify them. However, if those change for different reasons, then that is a false or accidental duplication that we are trying to avoid, which could cause issues when they change for different reasons in the future. In such accidental duplication situations, it is best to keep them as duplicates without trying to unify them. Next, there are three decoupling modes, which are source level, deployment level, and service level. In source level decoupling, changes to one module do not force changes or recompilation of other modules. All the components share common address space and communicate with each other using function calls, and generally less intra-component communication happen over network. This is usually called a monolithic structure. The next extreme of decoupling mode is the service level decoupling, where we reduce the dependencies down to the data structures level and the majority of communication happen through network. In today's world, we can identify modules that communicate with each other using their own APIs. Deployment level decoupling is somewhat in between the source level and service level. Yes, in this level too, source code changes of one module do not force changes in another module. But the most important thing in deployment level decoupling is that decoupled components are partitioned into independently deployable units such as jar files, DLLs, or NPM packages. Technically, there is no single best decoupling mode for all the use cases. It is always best to leave the decoupling mode open for the evolving changes. What I mean by that is, given a delete employee use case, at the initial stage of the project, it may sound logical to do the decoupling at the source level, and when the project matures, it would make more sense to decouple at the service level. So we are keeping the decoupling mode open throughout the life of the project. Now let's get on to some action steps. First of all, I want you to identify what are the components and modules in your architecture that do not support operations, maintenance, development, and deployment. If you have any component that takes so much time and effort to build a simple feature, that means it does not support maintenance and development. Do you have any component that requires manual script running or manual secrets to update before the deployment? Then those components do not support deployment. So identify those components in your architecture. Next, check if you have unified modules that change for different reasons. Then it is a case of accidental duplication. When you have these problematic components, now is the time for you to determine the best way to decouple them, either using layers based on use cases or using different modes. Also think about how you can keep the decoupling mode open for future changes. However, always remember, do not over-engineer. Finally, when you get to design a new system, do not plug and play an old architecture. Think fresh in terms of use cases, development, maintenance, operations, and deployment, and build a new architecture which leaves options as open as possible for as long as possible. This wraps up our discussion on good architecture and decoupling. And if you like this content, please like, share, subscribe, and comment with your ideas and other topics you would like to learn in the future. Thank you for joining. See you in another video. Until then, happy coding.